The next speaker is also a friend of mine. He's also, just as Charles, we've also worked together on quite a number of projects, and I know many of you know him. He's a bit noisy, especially on Twitter. So I won't say much about him. I'm going to introduce Trevor, who's coming to not just blow some fuses in our brains, but he's going to talk about some complicated stuff, which I should be taking a seat so that I can also gather as much as I can. So let's welcome Trevor Saudi.
And what importance this presentation will be for you all. So I mainly picked this topic because of the budding interest I'm growing in reverse engineering and exploit development. It was inspired by an actual CTF I played a while ago and an amazing write-up I came across by my good friend Gilbert Robert. So I did more research about it, ended up learning a lot. We'll talk about a real-life example. I'm going to discuss concept of execution paths, take you through the first demo, talk about the problems of symbolic executions, and bring you to the final demo that showcases how to get around the same problem. So if you have your laptops, be prepared to get your hands dirty if you want to code along with me. So what is symbolic execution? Does anyone from the audience have a clue? I try to make this interactive. There'll be rewards if you answer questions. Anyone has an idea? Okay, so symbolic execution is a method of testing programs where instead of supplying normal inputs, we give the program symbolic inputs that represent arbitrary values. Might sound a bit convoluted, but let's think of it like this. Symbolic inputs, these symbolic inputs that I'm talking about are like abstract values, like variables. So what I essentially mean is that we look at inputs as abstract values, like x, phi, lambda, sigma. Another way to think of it is basic algebra. Take you back to class 4 or 5. You can have a simple equation, x plus 4 equals to 8. There are several ways of solving this equation. If you are to solve it statically, we can say, let's iterate through all the values of x so that you can satisfy this equation. We can do a 1 plus 4 equals 8. Compare 1 plus 4 is 5, it's not equal to 8. 2 plus 4, 3 plus 4, 4 plus 4 till we reach 8. But there's another more efficient method of solving for x. We can rearrange the equation and solve for x. Say something like x equals to 8 minus 4 gives you 4, and we satisfy the equation. So, in symbolic execution, x is going to represent our symbol, and this particular symbol is bounded by what we call an execution path. It's like a road we follow that is going to take us to 8. We have x is going to equal some particular value, and this value is going to lead us to an output which is 8. So that's what symbolic execution does for us. It walks us through the various execution paths that would lead to our output. So what about the second example? X squared plus 6x plus 18 equals to 12. If we tried to go through all the values of x, we start with 1, we start with 2, we start with 3, we go on, we might probably take millions of hours to solve this equation. It wouldn't be feasible because we are doing it statically. Jolene talked about static analysis of code. There's a question I wanted to ask her, but I saved it for this session, and you'll see what I mean in the next slides. So this is an example of a static way of testing code where we provide input values ourselves. So if you've used Python before, JavaScript, whichever languages, we have this assert almost equal, you can say think assert equal, and what it does is it's going to compare, you can see here we have 2,8. So basically your cuboid volume, it's a function, does something, probably calculates cube of functions, or maybe finds the area of a cube. So if it was a function and it takes two values, the top, as parameters, we're going to supply them as 2 and 8 in our self.assert almost equal, and you're going to test this particular function and see if, in this case, assert almost equal is going to check if these two values are almost equal. So we are testing statically, or providing the input values ourselves. That's static testing. So we now have a general idea of what symbolic execution is. We are not providing inputs to programs, rather we are going to solve them symbolically. We are going to analyze the various execution paths that programs have. We'll see this in a couple of slides later. And let's go on to why this topic is important. So for a fact, as Alfred or Ilan mentioned, we have thousands, possibly millions of programs being created every day. We use these programs to solve problems on a daily basis with help from computers. But to actually solve problems well, we need reliable programs, right? So there is a large-scale production of programs for a fact, and manual static analysis may be infeasible. If you're dealing with millions of lines of code, it might be hard to test manually, giving input, check the output, generalize and maybe say for positive integers, this is the output we expect. But what if instead of analyzing the inputs, we analyze execution paths? Again, I'll show you what execution paths are. Execution paths are basically, like I said, they're basically like roads that are going to lead you to various destinations. Destinations could be an output for a program. If we analyze these paths, we can infer how programs are going to behave and make techniques like debugging, reverse engineering easier. So an example of this destination or end goal that we may want to achieve is finding a part of code that is going to violate an expected output. Let's say I have a function that is going to maybe perform some mathematical operations, and I made an error when writing the code that doesn't account for a division by 0. It may be hard to test this manually using such a method, going through maybe negative values, positive values, integers, and so on and so forth. Instead, we can analyze execution paths and see it will make more sense than the later slides. So I have an example here where in the year 2014 we had a famous bug, and this is a block of code that caused the bug. I'll give you 1 or 2 minutes to tell me where the bug is and what it might cause. And if you get it right, I have a reward for you. Sorry? Yeah. Okay, if you look at the code, the offender is the second go-to fail. This one that I've clearly highlighted for you. Go-to fail. This second go-to fail, what it does is it's always going to be executed, whether the function fails or it passes. So What that means is all this code that is here, the important code that is here is going to be skipped. This was in the Apple's SSL implementation in 2014, where we don't know if it was an intentional mistake done by a developer, but it has very serious implications, because if this SSL raw verify is skipped, that means we can't effectively verify SSL certificates, and an attacker can craft a legitimate certificate, create a malicious website, and orchestrate a social engineering attack like what was happening with Uber. So one of the key applications of symbolic execution is to catch programming errors. Joylene talked about SNCC and CodeQL and the various implementations that are there. But for symbolic execution, what we are going to do is we are going to automatically discover this error. How? We have various functions. Think of the functions like states. If this SSL raw verify is a state, and we can analyze the execution path that takes us to this state and figure out that we actually can't reach this state, then we can begin to look for why. Why can't we reach this state? And if you go back there, you'll figure out that go to fail skips all this and we can't reach some states in the program. That's what symbolic execution is going to help us with. So I've mentioned a lot about execution paths. An execution path is how you traverse a program to reach a given state, where, as I explained before, a state could be an output that we want. It could be a successful returning from a function, and so on and so forth. We have this simple program. It's a Python pseudocode or a Python program that asks us for an input and prints either success or try again. So if we were to break it down in terms of execution paths, we'll have two execution paths, success and try again. We have a stage that will take us to try again, and one will take us to success. So the input that we are talking about is going to be a symbolic value. We will supply, let's say, pass 1 to 3 in this case. We look at it in terms of symbols. The input will be a symbol, and it's going to represent our input variable. So in this execution pathway, arriving at success, and what the various libraries that I'm going to introduce you will do, it will walk us back and try to figure out, using some very complex operations, what input will trigger this particular execution path. But I've shown you a trivial example, but what about this example here? I don't know if the code is legible, but the first lines of the code are very complex mathematical operations. We do some shifts, some XORs, and whatnot. If I asked you to reverse this by hand and tell me what the input will be, it will probably be very difficult for you. You might not get the answer, but this can be represented in terms of execution paths and the various states that we are trying to reach to. And if we have the appropriate tools, we can try and backtrack and figure out what the input is. So for the, assume in this example, our input is also represented by lambda. And to find this value of lambda, as I said, we walk back our execution path using very complex techniques. An example of this complex techniques is called the satisfiability modulo theory, or SMTs. This is the core that drives the Z3 tool if you've ever used it before. It's basically proving that mathematical formulas are satisfiable. So now connect the dots with this and the algebra example that I showed you, where we are trying to prove the x plus 4 equals 8. We are trying to satisfy the equation. So if it were more complicated, we are going to introduce things like the SMT theories that walks back and does the various calculations for us. And a good thing is that we have tools that abstract these SMT solving methods, such as anger. So we don't have to figure out ourselves what is happening behind the screens. Anger is a binary analysis framework. I'm sure if you play CTFs, handle reversing, you've probably heard of this. It's a binary analysis framework that is based on a suite of Python 3 libraries that allow you to carry out various execution tasks the various tasks like static and symbolic execution or analysis of programs. So the interesting bit is here now. We're going to get our hands dirty. Our lab is going to be based on binaries provided to us by the guys that made anger. Okay.